Preparation of alkenes. There are two ways to prepare alkenes, which are dehydration of alcohols and dehydrohalogenation of haloalkane. In dehydration of alcohol, the reactant is alcohol. This is a compound with hydroxyl group, which is the alcohol compound. The condition for this process are concentrated sulfuric acid or other strong acids and heat or reflux. So this is the alcohol compound. The OH group attached to one carbon, and at the end of the product, water will be removed. So that's what it means by dehydration, removal of water from the alcohol molecule. Water molecule consists of one hydrogen and one OH group. So the removal of hydrogen from this carbon and the removal of OH group from this carbon, resulting a product of alkene. The carbon-carbon double bond is the carbon which involves in the removal of hydrogen and OH group. Since initially this hydrogen attached to this carbon and this OH group attached to this carbon, so the double bond involved in the carbon-carbon double bond is the carbon that is attached to the hydrogen and OH group initially, and then the products are alkene and water. This is dehydration of alcohol. Next, the second way to produce alkene is dehydrohalogenation of haloalkane. Dehydrohalogenation means removal of hydrogen and halogen atom. The reactant is haloalkane. This is haloalkane. The conditions are base such as KOH, alcohol or alkoxide ion, heat or reflux. Here, reactant haloalkane. This X can be any group 17 atom, any halogen, and then the removal of one halogen atom and one hydrogen atom. So one halogen atom, one hydrogen atom. The carbon that is involved in the removal of atom, the carbon attached to the hydrogen and the carbon that is attached to the halogen. So for instance, in this haloalkane, this hydrogen is removed and this halogen X is also removed. So these two carbon are the carbon that attached to hydrogen and the carbon that is attached to the halogen. So these two carbon will form double bond at the end of the product. So it will form alkene and hydrogen attached to the halogen that is removed. This is dehydrohalogenation process. Saytzeff's rule. In an elimination reaction, the major product is the most stable alkene, commonly the most highly substituted alkene, which means when you refer these two processes, dehydration and dehydrohalogenation, these two are elimination reaction. Both eliminate water and hydrogen and halogen. So those two are elimination reaction. The major product of the reaction is the most stable alkene. Which one is the most stable alkene? The one that has most highly substituted alkene. If you focus on this carbon-carbon double bond, they are only attached to the hydrogen atom only. For this compound, this two carbon-carbon double bond has one substituted alkyl group, and then for this compound, two alkyl group attached to the carbon-carbon double bond. For this compound 3 alkyl groups attached to the carbon-carbon double bond, and the final one has 4 alkyl groups attached to the carbon-carbon double bond. So the more number of alkyl group attached to the carbon-carbon double bond, the more stable the alkene is. For instance, this is Saytzeff's rule. For instance, we have the alcohol compound here. The removal of OH group and 1 hydrogen atom, which is dehydration of alcohol process. In dehydration of alcohol process, we remove 1 OH group and 1 hydrogen atom from different carbon. So this OH group is removed from this carbon, and 1 hydrogen can be removed from this carbon, or this carbon. And then the major product is OH group removed from this carbon and hydrogen removed from this carbon here. And the product causes the carbon-carbon double bond have tri-substituted alkene. 1, 2, 3 alkyl group. So this is the major product because it has the most number of alkyl groups. For this minor, di-substituted only because this OH group removed from this carbon, and then hydrogen here, the hydrogen here is removed from this carbon, making the carbon-carbon double bond between these two carbon. So when the carbon-carbon double bond between these two carbon form, it only has di-substituted alkene. This is di-substituted alkene. 2 alkyl groups only attached to the carbon-carbon double bond. So this is the minor product. This is the major product. Major products means the product that has higher number than the minor product. So this is the example for dehydration of alcohol, means remove 1 OH and 1 hydrogen, means removal of water. That is dehydration of alcohol. Saytzeff's rule can also be applied for dehydrohalogenation of haloalkane. So this is the mechanism of dehydration of alcohol. Step number 1 is protonation of OH group. Protonation means giving proton to the OH group. Proton here is in the form of H+, means we want to add the H+ to the OH group. Here, at the OH group, at the hydroxyl group, we know that the oxygen is the electron-rich site. This is the nucleophilic site, electron-rich site, because this oxygen here have 2 lone pairs of electron. So the mechanism starts with the electron-rich oxygen attack the hydrogen in H2SO4. It attacks the hydrogen in H2SO4 because the hydrogen here is the electron poor site, because the O are the electron rich, so the electron poor is the hydrogen, electron poor site. So the oxygen from OH group attack the hydrogen in H2SO4. Fully headed arrow means 2 electrons are used to form bond with this hydrogen, and then this hydrogen now is sharing 2 electrons with oxygen. When this oxygen use these 2 electrons to form bond with the hydrogen, these 2 electrons here, the bonding electrons, 2 bonding electrons, are transferred to the oxygen in H2SO4. Both electrons transferred to the oxygen, making the protonated alcohol product. This is protonated alcohol, means add 1 H into the OH group. This is protonated alcohol, and HSO4 minus because 2 electron both on the O. So the minus here is at O, HSO4 minus. This is the side product, and this is the product of protonated alcohol. And make sure to write the plus symbol here because oxygen now need to share the electron with hydrogen, one more hydrogen. Oxygen prefer to have 2 lone pairs of electron, but now this oxygen has 1 lone pair only, means it has less electron than before. That's why this oxygen is positive. So this whole compound, we call it protonated alcohol. The second step is loss of water and formation of carbocation. So loss of water, the protonated of alcohol, we have H2O in protonated alcohol. Since this oxygen is positive, oxygen does not prefer to be positive, so it uses these 2 bonding electron, carbon-oxygen bonding electron. Both bonding electron is transferred to itself to the oxygen, making the oxygen have 2 lone pairs of electron again, and it makes a molecule of water. So this is loss of water and formation of carbocation. Here carbocation because this carbon lose its 1 electron sharing with oxygen, lose 1 of its own electron. Okay, and then making this carbon positive. We call this as carbocation. And the product molecule water here. This is the second step. The third step is removal of proton from neighboring carbon. Since this is carbocation, here, we have initially HSO4 minus. HFO4 minus here is nucleophile rich in electron. This nucleophile will attack the hydrogen in the carbocation, but the hydrogen is not the hydrogen that is attached to the carbocation. It is the hydrogen attached to the neighboring carbocation. Means this HSO4 minus will attack hydrogen which is attached to carbon beside carbocation. That's why the step 3 means removal of proton from the neighboring carbon. So attack, making this HSO4 minus H2SO4. The lone pair electron in oxygen used to form bond with the hydrogen. Both lone pair used to form bond with this hydrogen, and then these two bonding electron are used to form double bond between these 2 carbon because this carbon is positively charged. So it prefers electron to make it stable. So these 2 electrons are transferred between these 2 carbon, making alkene product and H2SO4. So this is the final step of mechanism of dehydration of alcohol.